Let's start with this example of computing derivative of a polynomial function. We can use definition of derivative to work this out. That means we have to compute delta y and then divide by delta x and then calculate the limit as delta x approaches to 0. That does work, but it is a rather involved process. What we are trying to do here is to develop some differentiation rules, so we can use the rules to determine the derivative without going through the definition. Okay, let's begin with the most basic rules here. Here we have derivative of a constant function is equal to 0. This is natural because a constant function has a graph that is a horizontal line, so the slope of tangent line should be equal to 0. Okay, and then derivative of x to the nth power is equal to n times x to the n minus 1. The way to remember this is to bring this n to the front and then subtract the exponent by 1. This is called the power rule. Okay, and then we have some additional basic rules. If you take the summation of two functions f and g and take its derivative, that is equal to the derivative of f plus the derivative of g. This is very natural to have. And then if you have a constant times a function, then its derivative is equal to the constant times the derivative of this function. In other words, you can take the constant out. All right. Now these simple rules are already enough for us to solve this problem. First, by this summation rule, you can just split this into derivative of the individual terms. And then for each term, you can take the constant out because of this property here. And therefore, this will give you the following. So for example, the first term should give you 2 times derivative of x to the 4th. Okay, and so on. Okay, and then for each of them, we can apply the power rule and then the constant function rule using for the last one. So x to the 4th power by the power rule should be 4, bring this to the front, then x to the 3 because 4 minus 1 is 3, and similarly for others. Okay, so x squared gives you 2x, you bring the 2 to the front, and then 2 minus 1 is 1, so x to the 1. And then x will give you just 1, because 1 times x to the 0th power. Here, x is x to the 1, so 1 minus 1 is 0. And x to the 0 is 1, all right? And then 16 is a constant, so the derivative is 0. And then this is your final answer, okay? Let's look at a few more examples, some very basic examples here. So if you take a derivative of 1 over x, although this looks like a quotient, but it's better to turn this into a power. 1 over x is the same as x to the minus 1. So basically you take a derivative of x to the minus 1, and then you can apply the power rule here with n being minus 1. Therefore, you bring minus 1 to the front, and then subtract the exponent by 1, and you get minus 2. Okay, so minus 1 times x to the minus 2, and then that is the same as 1 over negative 1 over x squared. Another simple function, square root of x. Well, again, this is the x to the 1/2 power, and then you apply the power rule. Okay, so x to the 1/2, and then bring the 1/2 to the front. 1/2 minus 1 is a negative 1/2, and then negative power just means you move this to the denominator, and then this is the final answer. Let's look at one more example. Here we have the following kind of fractional expression here. Well, we do not have the quotient rule yet. We're going to introduce that in the next slide. But really for this problem, it's better to just split this into two pieces. So we have 2 over x, square root of x over x. Each of the two can be solved using the power rule. Okay, so here basically you just write x here as x to the minus 1, and then square root of x is the same as x to the 1/2. Then if you multiply x to the minus 1 into here, then you just get 2 terms, each is a power. Okay, so you multiply this here, you get a 2x to the minus 1, and then x to the minus 1/2, because 1/2 minus 1 is minus 1/2. And then simply apply the power rule for each of them. Actually, those are exactly the function that we saw here. Okay. Well, the second one is next to the negative 1/2, so slightly different. All right, so first one, right, so bring the minus 1 to the front and then subtract by 1, you get a minus 2. For the second one, bring minus 1/2 to the front, because we had a minus sign here, so it's plus 1/2. Then x to the negative 3/2, because minus 1/2 minus 1 is minus 3/2. Okay. Next, let's look at a few more rules. The product of two functions, the derivative for that, this is called the product rule. So the derivative of fx times gx should be equal to f prime times g plus f times g prime. So first you take the derivative of f and then times g, and then you take the derivative of g times f. That's called a product rule. And then there's the quotient rule that we will see in a moment. Now the product rule allows you to compute derivative of our products. So here is one example. Obviously the first one is f, and then this is our g. So the rule says f prime times g. F prime in this case, it is just equal to 2x plus 0, so it's just a 2x, okay, times g. Okay, so this is f prime g. Then plus fx, which is right here, times g prime. G prime becomes 2 because 2x gives you 2 and then minus 1 gives you 0. And then you just simplify the algebra here. You multiply this into here and you get this. Multiply the 2 into here and then combine the like terms. So 4x squared and 2x squared are combined, and that gives you 6x squared. And then copy the rest. Okay. Let's look at the quotient rule. The quotient rule says f over g derivative is equal to the following fraction. The denominator is just the square of the denominator, so g squared. The top becomes f prime g minus fg prime. Okay, let's look at an example here. Here we have the following fractional expression. So this is a rational function. We want to find its derivative. So this is our fx, and then 2x plus 3 is our gx. We apply the quotient rule here. Therefore, we compute f prime. In this case, the derivative of 3x minus 2 is simply a 3. So 3 times g, which is 2x minus plus 3, minus fx, which is 3x minus 2, times g prime, and that is equal to 2. And then denominator is just the square of 2x plus 3. Now we're going to simplify the top, and the bottom is already in a nice form. We don't need to simplify. To simplify the top, you simply multiply this into the parentheses and then combine the like terms. So here's the result. You multiply this, you get a 6x plus 9, and then minus 6x, and then plus 4. Here we have a plus because you have a negative and a negative. And 6x and 6x cancel each other, and 9 plus 4 is 13. So that is your final answer. Okay. Let's look at this other example. We have x squared plus 1 to the 10th power. We want to take its derivative. You can multiply this 10 times to get a big polynomial, but it's better to do it if we have a rule for that. you can use the product rule 10 times, but again, that is a little bit involved. But notice this is a composition function. It's a composition function of x to the 10th and then x squared plus 1. And this brings us to the chain rule, which deals with a composition function. Suppose you have f composed with g. We want to take its derivative. And the rule says it is equal to f prime evaluated at gx, then times g prime x. Okay? So let's apply this rule to here. First, let's write down explicitly what f and g's are. In this case, f is just x to the 10th because this is something to the 10th. And then g is what's inside, which is x squared plus 1. So x to the 10 is our f, x squared plus 1 is our g, and we want to find out the derivative of f composed with g. Okay. Now apply the chain rule. It says we have to compute f prime evaluated at gx. Let's compute f prime. F prime is just a 10 x to the 9th. Okay. Now we have to substitute g into here. That means you have to replace x by x squared plus 1. So this is our f prime gx. And then you have to compute g prime. That is simply equal to 2x. Derivative of x squared gives you 2x, and then 1 gives you 0. And now you just put this into, apply the formula to here. So f prime gx times g prime. So this times that. Okay? And then just to simplify the algebra, you can multiply 10 to 2x, and that gives you 20x. Okay? And then x squared plus 1 to the 9. So that's the answer. Okay? Now, in practice, our function often is a composition of a power function and some other function. So like exactly like the case here, like something to the nth power and then gx. So in other words, the function looks like a gx to the nth power. And for that, we can actually write down a special case of the chain rule, and that is called a generalized power rule. So basically, if you have a gx to the nth power and apply the chain rule, it says f prime, so x to the nth power, derivative, that's n, x to the n minus 1. But then you have to replace x by gx, so you put gx here, and then times g prime. Okay, so this is the generalized power rule. This rule is much easier to use than the original general chain rule here. As long as our function is a power. Let's apply this rule to the problem that we just solved. So let's erase what we did and apply the rule so we can get the answer directly. Here we have a power of this function, so this is our gx, and then n is equal to 10. The rule says first you bring n to the front, so you put a 10 in the front, and then you subtract the 10 by 1, and you get 9. So you have 9th power here, and then times g prime, which is 2x. And then you simply combine 10 and 2 together, and gives you 20, and then, okay? So this is pretty easy to use. Let's look at the trigonometric functions. Here are the basic formulas for the derivative of those trig functions. I would say sine and cosine are the most basic ones that you must remember. The remaining ones can be derived from sine and cosine. Actually, we're going to derive tangent in a minute. So keep in mind, sine derivative is equal to cosine, and derivative of cosine is negative sine. Okay. With that in mind, we should be able to solve this problem. Here we have the product of sine and cosine. So we apply the product rule, which says if you take f times g, this is our f, and then g is cosine here. F g prime should be equal to f prime g plus f g prime. So first you take derivative of sine times cosine. Derivative of sine is cosine, so you just have cosine times cosine. This is your f prime g part. Plus f times g prime. F is sine g prime, so cosine derivative we know is a negative sign, so negative sign. And then just simplify the algebra. Cosine times cosine is cosine squared. Sine is sine squared, and that's it. Okay, this is also equal to cosine 2x, but it doesn't matter. We can keep the answer just like this. Let's look at another example, computing derivative of tangent using sine and cosine, so without using this formula. In other words, we want to derive this formula here. Okay, so remember, tangent is equal to sine over cosine. So this is our first step. You write tangent as a sine and cosine. We do that because we know the derivative of sine and cosine. Okay. So obviously this is a quotient. Therefore, we apply the quotient rule. Let's say the quotient rule says then the top is f prime g minus fg prime. So f prime derivative of sine is equal to cosine times g times cosine minus f, which is sine, times derivative of cosine, which is negative sine. And then the bottom is just the square of cosine. Okay. Now cosine is just cosine square, sine is sine square, negative becomes a plus. So you have cosine square plus sine square. And then there's a well-known identity, trig identity that says cosine square plus sine square is equal to 1. So we have 1 over cosine square. Now 1 over cosine is a secant. Therefore, this is also equal to secant square. So that's exactly what the formula says. Let's move to another example. Here is an example copied from the book. So we have the graph of two functions, fx and gx. And then we form composition functions. Ux is f composed with g. Vx is g composed with f. W is g composed with g. We want to find those three derivatives. Okay. Well, these are composition functions. Therefore, we apply the chain rule. Let's do the first one, u prime 1. So we have f composed with g. By the chain rule, it should be f prime evaluated at g. So g, g1, because x equals 1, times g prime at 1. All right, let's look at what those values are. First, let's determine g1. Okay, look at the graph. This is our graph, the black one. G1, so this is x equals 1, and then you go up and meet the graph of g. Looks like g1 is equal to 3 here. Therefore, we have f prime 3 times g prime 1. Now, what is f prime 3? Okay, look at the 3, 1, 2, 3. 3 is here. And we are talking about f prime at this point. Well, this is a straight line, so the derivative should be equal to slope of the line. The slope is equal to rise over run. And if you look at the x range from here to here, then you have a run of 4, and the rise is a negative 1. So it should be negative 1/4. That's your f prime 3. Okay, negative 1/4. And then g prime 1 here, okay, this is the 1, g prime 1. So it should be the slope of this line. And then if you look at the rise over run here, it looks like it's 3. It's minus 3 because it dropped. So minus 3 over 1. So it should be minus 3. All right, and the answer is just 3/4. Okay, let's do another one, v prime 1. So v is g composed with f, so g prime at f1 times f prime 1. What is f1? Well, f1 looks like it's equal to right here, which is equal to 2. Okay, so g prime 2, f prime 1. Now, what is g prime 2? Okay, g prime 2, x equals 2 is right here. Well, this is where you have a kind of like a corner point and doesn't have a tangent line. Indeed, the the derivative from the left equals to the slope of this line, and the derivative from the right is equal to the slope of the other line. They do not match. There's no tangent line here. Therefore, G prime 2 does not exist. And that shows V prime 1 does not exist. Okay. And then the last one, W prime 1, I'm going to leave it to you to determine. But the answer should be equal to -2. All right. These are all the examples we're going to cover here. Let me just end with a summary of the formulas that we learned. Okay, so here are the most basic ones: constant, derivative of constant, the power rule, scalar product, the summation rule, and then we have the product rule here, and then we have the quotient rule, and then we have the composition, the chain rule here, and also generalize the power rule, which is practically easy to use as long as you have a power function. Okay, and finally we have a bunch of formulas for the trig functions. These materials are not hard, but you just have to practice and practice.